Thank you very much, Michael, for the kind introduction, and indeed also for the invitation to talk to you today. It's a pleasure to be with you, at least virtually. And yeah, as I've said, I very much hope that we can have these occasions in person again in the near future soon. So yeah, my group is actually involved in quite a few different topics. As Michael mentioned, cold collisions between ions and atoms and neutral species is one of them. Another one is what we call molecular quantum technologies. And this is what I'm going to talk about today. So we'll talk about a new technique that we have recently developed, which allows us to detect and read out the state of a single molecule. And we developed this in view of performing very precise spectroscopic experiments on molecules. And so this will be the topic of my presentation today. So I will start with a short motivation on the topic, why we are interested in this. And I should also say from the very beginning that our single molecules will be molecular ions, which are confined in a trap. So we are talking about single molecular ions, which we are manipulating here. And in order to contrast what we are doing now, I will also briefly tell you what we did before, the old way, how we did state detection and spectroscopy. And that will form as a basis for the new scheme which we have developed in order to do this. And the big novelty will be that it will be in a completely non-destructive fashion. So we can do state readout and spectroscopy on a single molecule without having to perturb the state or destroy the molecule. And that is the big difference to before. And I will then discuss the prospects of this scheme in the framework of precision spectroscopy. So I will talk about clock transitions and a similar token about implementing qubits in the molecules we're interested in, and that is particularly N2+, the nitrogen molecular ion. And I will then finish with a short outlook. Good. So why are we interested in this sort of research, right? So I've already said that our prime motivation is to do precise spectroscopic measurements on molecules. And there are many applications for these precision measurements. I think Warsaw in particular is also a center for this topic on many levels. One of our motivations is in the end to develop something like a molecular clock. So the most precise clocks that we have these days are optical atomic clocks, but there are many good reasons to use molecules for this as well. So this is what we are interested in, among other things. In the same token, right, if you have a good system that provides a good clock, right, then it usually also means that it's a good system to implement quantum bits, right? So in this way, molecules are also an interesting platform for advancing quantum science. Then another thing that is also quite close to our heart is I think that the techniques that we are developing also have a lot of promise in chemistry and collision studies, right? In particular in state and energy controlled studies. And that is also something we're actively pursuing. And then last but not least, these precise spectroscopic measurements, they are these days used in many different applications to test fundamental concepts of physics. Right? One example would be, for instance, testing a putative time variation of fundamental constants, like the ratio of the proton mass to the electron mass, or things like this. Good. So I think one big advantage of using molecules for these sort of studies is compared to atoms, at least, is their sheer diversity. Yeah. So many of these applications that I have been talking about on the previous slide, they are these days pursued with various atomic systems, but the problem is you only have a handful of atoms available. And in contrast with molecules, I mean, you can have billions and billions and billions to choose from. And so you just pick the one that fits your purpose best. And in our case, this is the N2+ molecular ion. And it is attractive for our purposes because it is a symmetric homonuclear molecule. And that means that it does not have a permanent dipole moment. So it does not have a dipole allowed rotation spectrum. And it also does not have a dipole allowed vibration spectrum. So this means E1 transitions, so electric dipole transitions are forbidden, and you can only have either electric quadrupole transitions, so E2 transitions, or magnetic dipole transitions as the next order. And they are very weak and therefore narrow, but that is also because they are very attractive for precision measurements because they are so narrow. And because the molecule has no dipole moment, there are low systematic shifts on all these on these type of transitions. And so that is something that precision spectroscopists care very much about, right? To what precision can I actually measure a spectroscopic transition? And this is affected by, well, you know, the coupling of the molecule with the environment, right? And you can have things like Stark shifts of spectral lines, you can have quadrupole shifts of spectral lines, you can have shifts because of the interaction of the molecule with the ambient black body radiation field. And because this molecule is apolar, right, all of these sort of shifts, they are very, very small, and therefore it's a good system for precision measurements. The only thing is what you really need to worry about is Siemens shifts, right? And this is a topic I will come back to later. Another neat thing is that because it does not couple to dipole radiation, it also doesn't easily couple to the ambient black body radiation field. And this black body radiation field usually very often redistributes the populations of the molecules. And that is something that you don't want if you want to do experiments over a long time. And in molecules without a dipole moment, I mean, this is also automatically suppressed. This is also an important feature. And when we talk about N2+, right, the most abundant isotope is 14 N2+. So this means that we have, at least for the rotational ground state of the molecule, we have two nuclear spin isomers available, one with total nuclear spin quantum number of 0 or 2. And this gives you the possibility to either have hyperfine structure or not have hyperfine structure. And both are actually interesting for different applications. Okay, so after I've talked about the advantages of molecule, let me also tell you about the disadvantages, right? And this is why it has taken this field such a long time to develop, in fact, because if you compare it to atoms, molecules have quite a few drawbacks. They are complex, right? They have a more complex internal energy level structure, and that makes many technical tasks that you have to do in such an experiment more demanding, right? For instance, state initialization to prepare the molecules in a specific internal state is complicated by the sheer complexity. Also cooling, which is very important in these experiments. You want to work with cold samples, yeah, in order to suppress thermal effects as much as you can. It's also complicated because most molecules don't have closed optical cycling transitions that would enable laser cooling, right? Which is the working horse technique for atoms to get them cold. For the same reasons, these optical cycling transitions in atoms are also very often used for sensitive state detection. And if you can't laser cool molecules, then you also can't use these transitions for state detection. So you need something else. And the entire complexity of the molecule also makes the coherent manipulation much more challenging. So my group has been working on addressing all of these issues in the context of molecular ions for a very long time. And I should also say that we are not the only ones working in this field. As a matter of case, this field is growing rapidly right at the moment. There are many other groups who work on similar experiments, and this number of groups is ever growing. Okay, so let me just, before I show you some results, let me just briefly introduce our experiment. So I've already mentioned we work with molecular ions. We trap them in an ion trap. This is a so-called radio frequency ion trap that we are using. It's an assembly of electrodes to which radio frequency electric fields and DC electric fields are applied in order to confine the ions. What we usually do in these experiments, we have molecular ions, N2+ in our case, but we trap them together with laser coolable atomic ions. And these laser coolable atomic ions, they then work as a heat bath or a cold bath in order to sympathetically cool the nitrogen ions, because they themselves cannot be laser cooled, as I've already hinted at before. So we've already both species present, and then we have a range of different lasers. which serve the purpose of producing these calcium ions and also producing these nitrogen ions by photoionization in this trap. Then we have lasers for the cooling of the calcium ion and also for the coherent manipulation of the calcium ion. We have lasers for doing spectroscopy and coherent manipulation of the nitrogen ions. And all of these lasers, they are referenced to a frequency cone so that these lasers are also stabilized. So we then also have a microscope with a camera that is coupled to this ion trap. And with this microscope, we record these fluorescence images. What you see here is the fluorescence that's generated by these laser-cooled calcium ions, right? So they are constantly excited on an optical cycling transition. So this is why they fluoresce. And we can pick up the fluorescence of these species. And we can't see the nitrogen ions directly, right? Because they do not fluoresce, but we know that they are there, right? Because they do interact with the calcium ions. And this will play an important role in what I'm going to tell you over the course of my talk. Okay, so let me walk you through a few relevant experimental techniques that we need for these experiments. One of them is, of course, to produce these nitrogen ions, prepare them in a specific quantum state, and then sympathetically cool them by these calcium ions. And the method of choice in our case is state-selective threshold photoionization. In order to both produce the nitrogen ions in the first place, but also produce them in a very specific quantum state. So the idea behind this is that every optical process, like every optical process, also photoionization is subject to selection rules and propensity rules, and we can use them to our advantage in order to, when we produce molecular ions like nitrogen from their neutral counterparts, that when we remove an electron, we leave the ion that is produced behind in a specific quantum state, preferably the rotational ground state. So we have a tailored photoionization scheme that allows us to produce these ions in the rotational ground state, or in fact, also in any specific excited rotational state. And then we load these nitrogen ions into what we call a Coulomb crystal of the laser-cooled calcium ions. So we fill the trap with calcium ions, we laser cool them, and then they form these ordered structures in the trap. Here you see a fluorescence image of them, and these ordered structures is what we call a Coulomb crystal of these calcium ions. So the ions localize in the trap, and then they sympathetically cool the nitrogen ions, and the nitrogen ions, they intercalate in the center of this crystal. You can see this here as this ribbon, which actually does not fluoresce. This is where the nitrogen ions are actually located, and they are then surrounded by the calcium ions, which sympathetically cool them. Good. I should also say that there are other ways to start such an experiment and prepare molecules in specific quantum states, notably optical pumping, which can be preferably done on polar molecules. And these are methods that have been developed by a range of other groups in the field. Okay, so now we have prepared our molecules in a specific quantum state. We've cooled them sympathetically in our ion trap. Now we can do spectroscopy. And the important thing when doing spectroscopies is that in the end, you need to detect that the spectroscopic excitation has happened. And since we are only dealing with very few particles here, so in this Coulomb crystal that I've showed you before, we were typically loading some 30 nitrogen ions. One needs a sensitive detection technique to make sure or to establish that the spectroscopic excitation has actually happened. And in the early days, we used a chemical detection technique, alongside many others in the field. And our take on this was so-called laser-induced charge transfer detection. And it works in the following way. So it is well known, or it has long been known, that nitrogen ions, they can undergo a charge transfer process with argon atoms, but only if the nitrogen ions are excited to the first vibrationally excited state. So you can use this scheme then in a spectroscopic experiment to detect when you excite the nitrogen ions to the vibrationally first excited state. In the vibrational ground state, this reaction doesn't happen, and so you can discriminate between excitation and no excitation. And this is what we have done for quite a long time. So we started to take an interest in the infrared fundamental excitation of nitrogen. Yeah, as I've mentioned before, this is not dipole allowed, but it's allowed within the electric quadrupole approximation. So this is an energy level scheme of nitrogen. So you have vibrational structure, you have, of course, a rotational structure. Rotation can then couple to the electron spin of the molecule. You have spin rotational structure, and then you also have the nuclear spin, so you have hyperfine structure. And without going into too many details of this energy level structure, what we were interested in is the infrared fundamental, and we were then looking at specific hyperfine components of this infrared fundamental. And the experiment that we did was the following. So yeah, I should also say that this vibrationally excited state, this has a lifetime of about 160 days, right? Which translates into a natural line width of about 10 nanohertz. So because these transitions are electric dipole forbidden. And so this gives you an indication of how narrow these transitions are, but by the same token also how weak they are. Yeah. So they're about 10 orders of magnitude weaker than, you know, a decently intense infrared transition in a polar molecule. Good. So what we did in these experiments is we irradiated the molecules with a quantum cascade laser at 4.5 microns. So this is where this transition happens for several minutes. Yeah. And we really needed these long interaction times because, I mean, these transitions are so weak. And then we detected any of these excitation with this laser-induced charge transfer once the molecules were excited in the vibration excited state. And this is a typical experiment that we did at the time. So you see here is such a Coulomb crystal with the nitrogen ions in the center before excitation, before this laser-induced charge transfer. And then after this laser-induced charge transfer, you see subtle changes in the structure of the crystal, right? Because a few of these nitrogen ions had been excited and had undergone this charge transfer. So which indicated we had a spectroscopic excitation, but you can already see, right? I mean, it's only very few of these ions that did this because the transition is so weak. And you really had to meticulously go through these images in order to find out how many ions really reacted away. But one can then scan the frequency of the excitation laser, and what I show you here is a spectrum of specific hyperfine components of the infrared fundamental that we took with these methods. So that is already now more than 6 years ago. And back at the time, we were very proud of these results. To our knowledge, it was the first time that such a quadrupole infrared spectrum had been taken of a molecular ion, but it was painful. It was painful because it took us more than a year to find these extremely weak transitions, and then it took us more than half a year, I would say, to take this spectrum here, right? Because the duty cycle of these experiments is very low. Yeah, you destroy the molecules when you detect them, then you have to prepare them again, you have to cool them again, then you take several minutes to irradiate them. So it was very, very, very slow process to take these data. And as you can see, the signal to noise ratio is not great. Yeah. So if you really want to measure these transitions precisely, and that is our aim, then this is not the way to go forward. You can now say, okay, right? I mean, why are you only taking 30 ions? I mean, take many more, then you get more signal. Say, fine, that is something that one could do, right? But we then decided to do exactly the opposite. We took fewer ions, and as a matter of fact, we took only one ion. And we changed the detection scheme completely in a way which does not require us to destroy the molecular ions anymore by some chemical process when we detect the excitation. And what's more, we can also detect the quantum state of these molecular ions without having to actually to change the quantum state in any way, so that we can recycle the same ion over and over again. Then we only need a single ion, right? And we can do repeated experiments on this single ion all the time. And this then leads to improvement of the duty cycle by up to 5 orders of magnitude compared to what we did before. And as a nice thing is we also remove ensemble averaging, right? Because we are only dealing with a single ion, a single particle. And that is also an important aspect and a neat feature when you want to do precise measurements. I should also say that we are not the only ones working on these sort of ideas. The scheme that we implemented for our molecules has been inspired by similar experiments by the NIST group, who implemented something similar in the context of the aluminium optical clock some years ago. And there are also some other groups, both at NIST and at PTB, who pursue similar schemes in what is today known as quantum logic spectroscopy, which are related to what we are doing. Okay, so what we are doing relies on a state-dependent coherent motional excitation of the single molecular ion that we have in the trap in order to detect the internal state of this ion. So let me now walk you through slowly the different steps and the principle of this technique so that you understand how this works. So as in contrast to what we did before, we only work with a single ion, as already mentioned. And this single ion is then sympathetically cooled by a single calcium ion. So what we get is a calcium-nitrogen 2-ion string, as we call it. And the idea behind the whole scheme is that these calcium ions act as a sensor to what happens in these nitrogen ions. So the first step is to prepare such a calcium-nitrogen 2-ion string. And then we make this 2-ion string very cold, even colder than we do with just ordinary Doppler laser cooling. So these 2 ions are trapped in a trap, and this trap has a harmonic trapping potential. So we have like a harmonic oscillator, if you like, and then we operate the whole experiment in the quantum regime, meaning that the motion of these 2 ions in the potential of the ion trap can be thought of as a quantum harmonic oscillator. Yeah, we then get we then get quantized energy levels of this motion of these 2 ions in the trap, quantum harmonic oscillator energy levels, and then we can individually address these energy levels. And then we cool the motion of these of the 2 ions in the trap to the quantum mechanical ground state in this trap, by a technique called Resolved-sideband cooling that I'll explain a bit in more detail later. So now these 2 ions are in the motional ground state, and then we apply a 1-dimensional optical lattice. So this is 2 focused laser beams counter-propagating with one another, and the wavelength of these laser beams are tuned closely to a strong dipole allowed transition in this case, in the molecular ion. Yeah, so we are nearly resonant with a transition in the molecular ion, but not on resonance, so in order not to excite it, but just close to a resonance. What this then implies is that the energy levels of the molecule will, through the interaction with this optical lattice, gain an AC stark shift, a light shift, and therefore they also experience an optical dipole force, right, which is generated by the spatial variation of this AC stark shift within the optical lattice. And this is state dependent, right, because this optical dipole force only operates, right, if we are close to an optical transition in the molecule. And that is only the case if the molecule has been prepared in the correct quantum state for this transition beforehand. So in other words, we feel an optical dipole force if the molecule is in the correct quantum state. And if you don't feel an optical dipole force, then the molecule is not in the correct quantum state. Then the next trick that we do is we modulate this optical lattice at the frequency of the oscillation of these 2 ions in the trap. So when this optical dipole force is operative, then this modulation resonantly excites the motion of these 2 ions in the trap, so we heat them up again, if you like. But it's not a thermal heating, it's actually a coherent excitation. So this is why we call this coherent motional excitation. And then, once they have been emotionally excited again, we can do spectroscopy on the calcium ion to read out the excitation, this motional excitation that has happened. Yeah, and we can do this by what is called sideband radiothermometry on this calcium ion. So we probe the motional state of these 2 ions by doing a spectroscopic measurement, a Rabi flop on a spectroscopic transition on this calcium ion. And from this, we can infer the degree of the motional excitation. So in essence, this means the ions are cold in the beginning, motionally cold in the beginning. If the molecular ion is in the correct state, an optical dipole force becomes operative, which excites the motion of these two ions again. And this motional excitation can then be detected spectroscopically on the calcium ion. Yeah? So this is the basic idea behind this scheme. So let me show you how this works. So the first step is the preparation of this calcium-nitrogen 2 ion string. That is actually harder than it sounds, yeah, because the nitrogen ions, they are very hot to start with. They are formed from an ionization from a molecular beam effect. And they have a lot of kinetic energy, and this needs to be removed so that they can be cooled down. And if you only have a single calcium ion, right, then we don't have enough heat capacity to effectively cool this down. So what we start with is a big crystal of calcium ions, yeah, and then we produce only a single nitrogen ion, yeah, which is then sympathetically cooled into this crystal of calcium ions. You can see it actually here as a defect in this calcium crystal. So if you will, this is a very homeopathic experiment. Yeah? So we are only operating with a single molecule. And then we sequentially eject calcium ions from the trap until we are left with the calcium-nitrogen 2 ion string. So the next step is then to cool the motion of this calcium-nitrogen ion string down from the Doppler cooling temperature that we have originally down to the motional ground state of this ion trap. And we do this by resolved-sideband cooling, as I've already mentioned. So just briefly, this works as follows. So we take a narrow transition in the calcium ion. Specifically, it's the transition from the ground state of calcium ions, is a doublet S1/2 state, to an excited D state, a doublet D5/2 state. So this is also a dipole forbidden transition, but it's quadrupole allowed. So this is why it's narrow. So we can excite the calcium ion on this transition, right? And if we have a laser with a very narrow bandwidth, we can then resolve also the different motional states, right, of the ions in this trap on top of this optical transition in calcium, right? If you like, an analogy in molecules would be you also, excite vibrational levels, right, in an electronic transition in the molecule, right? So this would be an analog on here. And this is what such a spectrum looks like, right? So we have the bare electronic transition in the calcium ion, and then we have so-called sidebands, which correspond to the excitation or de-excitation of one quantum of the vibration of these two ions in the trap. So if we then keep pumping on the so-called red sideband, so that is a transition which de-excites the motion by one quantum, and if we do this repeatedly, then in the end we can transfer these calcium ions into the motional ground state of the trap. And since the nitrogen ion is coupled to the calcium ion by the Coulomb interaction, we also transfer the nitrogen ion into the motional ground state of the trap. So this is how this resolved sideband cooling works in the case of such a calcium-nitrogen 2 ion string. Good. So now we are in the motional ground state of this trap. As a next step, we can then apply this optical dipole force. And for this, as I've already mentioned, we need to put in an optical lattice, whose wavelength is near resonant to a strong transition in the molecule. And we chose the transition from the electronic ground state of N2 plus to the first electronically excited state of N2 plus, a specific vibrational component there. And of course, you also have rotational and fine structure transitions that you can choose from. So these are different fine structure components of this X to A vibronic transition here. I plot here the optical dipole force that we get as a function of the laser wavelength of this optical lattice. And you can see that close to specific resonances, this fine structure transition on these electronic transitions, the optical dipole force increases considerably. Yeah, and mind you, this is a logarithmic scale here. So what one can do now is one can pick one of these resonances, for instance, this R11 J equals 1/2 resonance. So this would be a transition in the molecule which starts from the rotational ground state, from the absolute ground state of the molecule to some component up here in the electronically excited state. So whenever the molecule is in this specific state, yeah, then the molecule experiences a strong optical dipole force if the wavelength of the laser is parked somewhere here, close to this specific resonance. And then we can do this coherent motional excitation trick. Yeah, and this is what you then get. And then we do again this, we look at the sideband transitions in the calcium ion in order to work out the temperature or the degree of motion excitation of this ion string. And we do this by doing Rabi flops on this quadrupole transition in the calcium ion that we have also used for cooling. And from the contrast of these Rabi flops and from the Rabi frequency, we can then work out the degree of motional excitation. And that here is such a Rabi flop on the calcium that you can see when the molecule was in the correct state. Yeah, so we see a clear Rabi flop here. However, if the molecule was not in the correct state, say any of the other states, then it doesn't experience an optical dipole force, hence no motional excitation, and then we do not observe any appreciable Rabi flop in this case. And so this would be such a background measurement. And this is here, it's a case when the molecule has been prepared in a different state, but the scheme still works on detecting the rotational ground state, and then we see if the molecule is in one of these other states, then we don't observe any signal. So we can discriminate in this way between the state that we are targeting and other states, and by changing the wavelength of this optical lattice, we can then essentially probe different levels in the molecule. Okay, so in order to do this state detection, one doesn't have to record such an entire Rabi flop all the time. It is sufficient if one just chooses the region of this Rabi flop where one gets the maximum contrast, say here, and do the measurement here, and then compare it to the background level. And this speeds up the measurement considerably, of course. So what sort of state detection fidelity does one achieve in this way? This is, of course, also an important question. And if one does a bit of statistics and math, then one works out that we can, in a typical experiment, we can detect the molecules in the rotational ground state with a fidelity of better than 99%, compared to when it's in any other state, which we can also detect with a fidelity of about 99%. And in this particular experiment, what has happened is the following. So we were actually probing this state all the time, yeah, and then it suddenly changed its state. So the molecule underwent a quantum jump, most probably because of an inelastic collision of this molecule with some molecule in the background gas of the vacuum chamber in which these experiments were taking place. Yeah. So and this also shows that we can track state changes of the molecule over time in this manner. And this is also quite a nice feature, which I will come back later a bit as well. Okay, one can also use this for spectroscopy, actually. Spectroscopy is in the end about detecting changes of quantum states in molecule, right? And if we change the quantum state now, we can use this for spectroscopy. But one can also use this AC Stark shift and the dipole force that's generated as a means to do spectroscopy in a way of what one could call force spectroscopy. Like, the transition, the optical transition that we use in the molecule to generate the optical dipole force, we can actually map this out by changing the detuning of the optical lattice from this transition, and thereby record like the strength of the optical dipole force as a function of the detuning of the laser wavelength from these transitions. And this allows us to map out the line shape of the spectroscopic transition. And from this, we can then extract, well, the resonance frequency and also quantitative spectroscopic information like Einstein A coefficients, transition moments, if you like. And one can then compare this to literature values in both cases. And we can see that, this is also a very adequate means to get line positions and transition strengths in that way. Okay, so how am I doing time-wise? How much time do I have, by the way?
I think 10 minutes, because it
10
should be
minutes, okay.
45 minutes in total.
Okay, very good. Then in the interest of time, then let me just skip the next few slides and maybe come to this point now. So what I have shown you so far is a new scheme which one can use to detect quantum states of single molecules, and it's totally non-destructive. I should emphasize this again. It doesn't destroy the molecule, and it also doesn't perturb the quantum state, right? Because the molecule is never excited. It's just used to create an optical dipole force. But in terms of doing precise spectroscopic measurements in this molecule, nitrogen N2+, the question is what transitions in this molecule are really suitable for precision measurements. And this is again a schematic or an excerpt of the energy level structure of N2+, showing the complexity from which you can draw on, right? We have low vibrational structure, we have fine structure, we have hyperfine structure. And in principle, you can think of studying different types of transitions, right? You can study hyperfine transitions, you can study rotational transitions, you can study vibrational transitions, you can study spin rotation transitions, all these sort of things. And the question is which ones are interesting. And this is for precision measurements. And this question then also relates to, okay, which of these transitions are very weakly affected by environmental perturbations? In other words, which of these transitions have low systematic shifts? And I've already said in the beginning that Stark shifts, black body shifts, quadrupole shifts, they can all be very, very low here in this molecule. What one needs to be careful about the Siemens shifts, right? Because it's a paramagnetic species, it has an unpaired electron, so it interacts quite strongly with magnetic fields. Yeah? And so magnetic field perturbations will therefore be the main cause for imprecisions in spectroscopic experiments on this molecule. So by the same token, if you have found a good spectroscopic transition, which is only very weakly perturbed by magnetic and other fields, then at the same time you have found a good transition to implement a molecular qubit. Yeah, because energy fluctuations which lead to spectroscopic imprecisions also lead to decoherence in qubits. Yeah? So this is two sides of the same medal. If you have a good transition for precision spectroscopy, then you usually also have a good qubit. Okay, so let's have a look at a few of these transitions and see how suitable they are for doing precise measurements. Let's take as an example hyperfine transitions, or hyperfine Siemens transitions, I would say. In this molecule in the rotational ground state. And what you see here is essentially a study of the Siemens effect of these transitions between two hyperfine levels in the rotational ground state. We have a range of Siemens transitions, but the point being is that because the energy level structure is so complex, right, you have many interactions between the levels, and the Siemens effect is not linear. And in particular, this means that you can find certain magnetic fields at which the sensitivity of a specific transitions, like those here, is insensitive to changes in the magnetic field to first order. So in other words, the derivative of the Siemens energy with respect to the magnetic field is zero. So this means that this transition only very weakly reacts to fluctuations of an external magnetic field. And this is experimentally a major nuisance. So this means that you can find certain magic magnetic fields, as they are called, right, at which certain transitions, yeah, essentially only very, very weakly react to fluctuations of the external magnetic field. Yeah, and so these are conditions, transitions, and then specific magnetic fields which are very amenable to precise measurements on, say, hyperfine transitions. You can also think of rotational transitions. You can also find quite a range of magic transitions in the rotational structure of this molecule. Here I'd like to make a different point. If one just looks at fine structure transitions, yeah, so this would be transitions from, say, the rotational ground state, and the J equals 1/2 level. So J is the quantum number that, well, it's the total angular momentum quantum number of the molecule, including the nuclear spin. And if you just then look at excitations to, say, the second excited rotational state, and then a specific fine structure component here, then you can look at so-called stretched Zeeman transitions. Yeah, so these would then be transitions from a magnetic quantum number of, say, +1/2 to a magnetic quantum number of +5/2. Yeah, so this would be the extreme case for a Zeeman transition on this specific transition here. And as it turns out that these stretched transitions, they also have a very weak dependence on the magnetic field over a wide magnetic field range, actually. So they show a perfectly linear Zeeman shift because they do not interact with appreciably with other levels. And the Zeeman shift is very small. Yeah, so these are also transitions which are quite attractive for precise measurements. And last but not least, the transitions that we are particularly interested in, so vibrational transitions. Again, you have a host of transitions that you can choose for it if you want to do a precise measurement. And you can also find a large range of different magic conditions, magic magnetic fields, where many of these transitions become first order independent to magnetic fields. Yeah. So the take-home message here is that the complexity of the molecule, right, actually is an advantage here, right, because you have many different transitions to choose from for precise measurements, and you can choose just the ones which which are most adapted to your specific purpose, right? You can look at hyperfine structure transitions, rotational transitions, and vibrational transitions, and in every case you find transitions with excellent properties. Okay, so what are we going to use all of this for? So our ultimate aim is as I've already said, we want to do precision infrared spectroscopy, nitrogen plus, and then one of the motivations for doing is as I've said in the beginning, one could think of implementing an infrared molecular clock in that way. And we're now going to use our coherent motional excitation detection scheme to do essentially the experiment we did before, but just much more precise and much more sensitively. And what we'll do is, this is a type of depletion spectroscopy, if you like. Yeah. So the experiment that we have done so far is we've prepared the molecule in a specific state, typically the rotational ground state, and detected whether the molecule was in this rotational ground state with our detection scheme. Now, if we then add an additional infrared laser to excite the molecule to the first excited vibrational state, so that's the spectroscopic transition that we are interested in, then the molecule is not anymore in the rotational ground state, right? And so this means that we will not observe a coherent motion excitation signal anymore. So in this fashion, one can do what is called depletion spectroscopy, and detect an infrared spectroscopic transition on the single molecule. Yeah. Then you have excited the molecule, right? In the end, you need to bring it back to the rotational ground state again so that you can do the experiment over and over again. But this will then be the scheme with which we can do the spectroscopic experiments on the same molecule all the time. Good. Another important aspect of this is that if you want to do a precise measurement, you need to be sure that you are precise. And this entails that you have to compare yourself to another precise frequency measurement. And ideally some primary frequency standard, meaning some atomic clock. Now, an atomic clock is not something that you usually have in your cellar. This is something that's run by national metrology institutes typically. And in Bern, we have the Swiss Federal Institute of Metrology METAS, which operates the Swiss primary frequency standard, which is a rubidium fountain. And we are now in the process of, or not in the process, we've just completed this actually, of implementing an optical fiber network that connects us and also other spectroscopy laboratories at ETH in Zurich with METAS in Bern, so that we can reference ourselves, our measurements, to the Swiss primary frequency standard. And that is will be an important aspect in validating the precision of our measurements in the future. So this frequency transfer, this is now operative. Also here in Switzerland, also many other countries have implemented similar schemes very recently, and this will be an important element for all sorts of future precision measurement. So at the very end, I would also close the circle and come back to the cold collision studies that our chairman has mentioned in his introduction. The scheme that we have been developing, I think it's not only attractive for doing spectroscopy, but I think it will also have some exciting applications in collision physics and also in chemistry. And this brings me back to some recent work that we have done together with our chairman recently, with Michael Tomsa, where we studied cold collisions between the nitrogen ions and rubidium atoms in millikelvin collision energies. And the objective of this particular study was to study charge exchange collisions between these two species at very low temperatures as a function of the internal state of the rubidium. And it was quite an interesting study. We learned quite a lot about it, about very fundamental aspects of charge exchange, last but not least with the theoretical help of Michael. But there was one drawback of these studies in the sense that the nitrogen ions were not state prepared. Only the rubidium atoms were state prepared. And but with our new scheme, right, we can make sure that the nitrogen ion, and in this case it will be a single nitrogen ion, will be only in a single state. So we can also do state-specific studies on nitrogen, on the molecular side of these experiments. And if this was about charge exchange collisions, but you can also think of other processes like inelastic collisions. And with our new detection scheme, we can track as a function of time when the molecule changes its state over the course of a collision, right? We've actually already done this, right, in the previous experiments. But in principle, one can also do this in a much more controlled way at very low collision energies. And this is also an application of this scheme that, and an extension of this detection scheme that we are currently working on. Now, let me wrap up and summarize. I have presented a new method which allows us to non-destructively detect the quantum state of a single molecule without destroying the quantum state or even the molecule itself. And it works by coherent motional excitation using a state-dependent optical dipole force. It's quantum non-demolition, and it's therefore highly sensitive, much more sensitive than the previously used chemical detection schemes. And I really see it in a way as this coherent motional excitation for me it's a counterpart to the state-dependent fluorescence that is used in experiment with atoms to enable a sensitive state detection. Yeah. And so in a way, one has now found a counterpart in molecules for the state-dependent fluorescence in atoms. And as I've shown you, it enables us direct measurements of molecular transition moments and also transition frequencies. And I foresee applications in precision spectroscopy, state-to-state chemistry, and also in quantum technologies, if one is interested in that. And with that, I'd like to finish. I'd like to thank my group, who is doing all the work, in particular the team which worked on these specific experiments. So Dr. Sif Meir, he's a senior postdoc on this project, and he's doing these experiments together with a range of very gifted PhD students: Gregor Hegi, Kavena Chavian, Mikolaj Rorushki, Alexander Shlykov, and Moody Zinhal. So all of this would not have been possible with the hard work of all of these people. I should also thank our sponsors. And last but not least, I also thank you for your kind attention and for the invitation to give this presentation today. Thank you very much.
Yes, so thank you very much, Stefan. It was very inspiring talk.